I don't know. Where was I? So sorry. Uh, oh, was technical problem. Um. So I think here. So we have in this case we have raw materials that we have to pay for, and then we have the design of the plant itself that we also have to pay for, and then we need to produce. I mean, we need to use some form of energy, and then water, yeah, or solvents, and then we by having all of this that we are paying, we
Can
will
you
be
share
able
your
to
screen?
produce a product, and then which has a price to it, yeah. So we can generate money from this product by selling the product, and then together with the products we may, definitely in most cases will produce like byproducts. So these byproducts we will either have to treat it, or we'll have to pay penalty for that, yeah. So the
Excuse me.
goal in all optimization is about to maximize the profit. So that profit is basically,
Papa?
hello.
Yes, could you share your screen?
I share my screen. See now. I did not share my screen. Okay.
That you can share your screen.
You have to quickly save this because I am um um yeah, good. So if you have any question, just interrupt me. Yeah. If you have any question, just interrupt me. Um. So the formulation again, the formulation for all of this is to maximize the profits, and then that profit is in this case if we sell our products, and then we have like some sales value, and then we minus the sales with the raw materials that we are consuming, and then minus with the operating costs, and then minus and everything, and so on and so forth. So in the end, we were left with some amount of money, which is then the profit. So in this case, the objective functions, we typically write this in this way. So objective functions then are functions of the amount of the product, the raw materials, energy, water, solvent, and so on and so forth. Then the optimization is then in this case to find, if we take into account the design of the plant. So it's basically to find the set of the design criteria, like how big is how big is the distillation column, how big is then the reactor, what type of catalyst, and so on and so forth. And then what are the operating variables like the flow rate, pressure, temperature, in such a way that it will then yield a maximum value or optimum value of the objective function, which is in this case the profit. So there are, as you know already, there are several parts, essential parts for optimization. So number one is that the objective functions, which we know already by now, which is the profit functions, yeah. And then there are also like cost function to minimize costs and so on and so forth. But we don't use this quite often. So what, because we care about to make money. That's what we do in the industries. And then there are several constraints because we cannot simply use as much raw material as possible if we want to make more product. So there are constraints. The first constraint is that the design variables constraints. I mean the design the condition constraints. So I've said that we need to there is like an upper limit, right, for the raw materials, or how much product that we can make because of the design boundaries. And then we have also like constraints like a mass and energy balance constraint, right? So what comes in should comes out, that is then valid in terms of energy and mass. And then there are also constraints on the laws of physics and thermodynamics, yeah, right? If we put in like a certain amount of crude, and then we heat it up to a certain degree C, and that could contains like properties that we know already like last time. So it can only produce some amount of gasoline, some amount of diesel, and so on and so forth. So we cannot make more gasoline than what the crude can have. And then we have also like inequality constraints. So equality constraints means in this case it comes so as equals, yeah. So equals. So inequality constraints is then the operating variables. So for example, that feed flow rate should be then bigger than a certain number, and then the lower than a certain number. Yeah, so that's basically the constraint. And then variables, for example, yeah, we want to design the reactor with the length of the same case bigger than or equal to, and then lower than or equal to a certain degree. So basically, as we know this, so this then the in equals to out, yeah, in equals to out for whatever either it is mass or energy. These are all like mathematical models that we have to have or we have to put in place before we can do any optimization in this case. Think I've mentioned this. So in general, if you go for like a in textbook or whatnot, so in general, the generic mathematical programming for optimization, it starts with minimization. So in this case, we minimize an objective function. If we were to maximize profit in this case, so that means typically behind the scene, it will then minimize the minus of that objective function, minimize the minus of that profit. Yeah, minimize the minus of the profit, which makes it maximizing the profit. And then we have to obey the constraints that we know already. So the h equals to 0, which is then the equality constraint, and then the g less than or equal to 0, which is then the inequality constraint. In this case, x is then the typically continuous variables, y is then the binary variables, and we have a certain like called z, which is typically used for integer. Yeah, for integer. So z is then the integer. Constraints, I will skip this one. Yeah, I will have to share this with you before we go to the example. So this is my experience. I compile this with the some information from the literature. So number one, to be able to yeah, to be able to how to develop and solve optimization problem. In this case, number one, we have to fully understand the problem at hand. We have to fully understand what do we want to solve, or what do we want to to obtain. So if you don't if we don't if you don't fully understand what the problem is, it's going to be very difficult for us to formulate the problem. So if you cannot formulate the problems, we will not be able to solve it. I think you know this from your experience as well. But nonetheless, and then what people don't realize is that this is not a once through. This is not a once through kind of process. This is a back and forth discussions. Yeah, as you know it. And then from once we understand the problem or the process, and then we will then start to writing down what is exactly the objective function, and then we break down this objective function into several elements. So the first case is that, for example, that profit, it comes from making the product minus the operating cost and then the raw material cost, and then we can then model, okay, that making the products, how much will it be, and then how we will get that product, and then the same goes with the sales. I think I will have to write it down so you can have the idea. Okay. Oh, sorry. Um, where's my pen? Some paint. Say, for example, you have the objective functions. So your objective functions, you have you maximize your profits, right? Profits, and then you can say, well, what constitutes this profit? So profit. So this is then your objective functions. So this is number one, and then number two is then your constraint. So basically, your profit equals to your product price, product sales, right? So this is your first equality constraint, yeah, your first equality constraint, that H1, and then this equals to product sales, and then you can also say product sales equals to sales equals to product times the price itself. So this is then your the second equality constraints, and then you can say, okay, now product equals to for example, the yield of your raw materials times your raw materials, and you can know that this is operational data, right? This is something that data, and then this is another variable that I can write down. So profit in this case is then product sales minus the I forgot to put the minus. So product sales minus the raw materials, and then minus the operating costs, for example. Yeah. So this raw materials is there over here, and this is also like a variable that we want to find, variable. And then operating costs, for example. So operating costs equals to, obviously, so just make it simplified. So it's then the raw materials times a certain constant, yeah, I don't know, and then this then your operational cost, and then you can also say that this is an raw material cost, right? So your raw material cost equals to your raw material basically times the cost, right? So you have already write down several constraints, and then you can also say, okay, raw materials based on the current plant can be that bigger than 10,000, for example. I don't just put some number, and your product can also be like in between, like I don't know, maybe 6, 7,000, up to you. Yeah, depending on the circumstances that you have on the field. Um, is that clear? Okay. So I've shown you these variables and parameters, and then you could also use mind maps here. When you develop this problem, you can use mind maps. Then you can then see, because everything here, this profit is basically your what we know in modeling. Your profit is basically your dependent variable, or y, dependent variable. And then the raw materials, or your variable here in this case, is your decision variable, or your independent variable. Yeah. So this is then your independent variable. This is your dependent variable. So if you then generalize it or make it in general form, you could then say, okay, my y equals to as a functions of all kinds of x. So your x is then your independent variable or decision variable, and then your y is then the things that you want to see or evaluate. So in this case, your profit. So you will need to be able to, using the solver of the optimization, we will then try to find what is then the optimum x in such a way that y is then going to be maximized. So that's basically what this is. Where's my mouse? Okay. Yeah, I use mind maps, and then and then once you get the model, and then you have to check the model whether it makes sense or not. Yeah, it cannot violate these all of these laws of physics and thermodynamics, all of these mass and energy and momentum balances. And then once we get all of these once we get all of these once we get all of these five basically, we will then, depending on what the problem looks like, we can then apply suitable optimization technique to solve the problem. If it's too complicated, we will then try to simplify it as much as possible. Okay, and then once we get a solution, we'll then have to try to do sensitivity analysis on the results or on the parameters itself, because all of these parameters, the parameters like the data, like yield, the example that I put to you, yield is not really a constant value. So depending on the all kinds of circumstances, it can vary from one position to the other position. So we will have to then try to rerun this model several times in such a way that we can then see what would be the range of profit if we were to adjust the yield from a certain value to another value. So that's basically what that is. Now, we have this. I think you have it also in the slides, but try to think first. So if we, for example, yeah, um, so we have a process stream. It comes at 170 degrees C, and then the flow rate is 500 kilogram per hour, and then the CP value of this stream is 1 kilojoule per kilogram degree C, to make it simple. And then we want to cool it down to from 170 degrees C, we want to cool it down to 80 degrees C. Okay, want to cool it down to 80 degrees C, and we have to do that. We have a flow rate of water in this case, and it has this because how do we know this water? We know from this number. So the CP of 4.2, and then it comes at the ambient like 25 degrees C. So the question is, if we know the cost, so that exchanger, this heat exchanger, if we know the cost of the exchanger, which is that the a constant A times the area of the heat exchanger to the power of 0.84, and then the overall heat transfer coefficient of 1000 watt per square meter degree C, what would be the optimum size of the exchanger, and then what would be the cost, and then what would be the outlet temperature of the water, yeah, outlet temperature of the water. So I think you can spend give you like 5 minutes or so. Just try to spend 5 minutes to write down the objective function, equality constraints, inequality constraints, and variables, and then that will yeah, I will call you out loud, so that you can yeah, at least explain to the team what you think on each of these four items. So we are now like 242 quickly, 247 will then we'll discuss this. If you think you need to ask something, just ask. Yeah, just ask. Okay. So now, anybody wants to share what the objective function is? Um, yeah. Daniel.
Hi, Doctor. Objective function, I think, is to um, minimize the use of water.
Okay. Only that. Sujendran.
Hi, Doctor.
Yeah.
I would think that the function will be on minimizing the capital cost for the exchanger.
Okay. So Daniel says it's minimizing the cost of the water. Sujendran means minimizing the capital cost. And Muhammad. What's his? What's your Muhammad Zuhafiz?
I think as minimize the temperature and the efficiency.
Efficiency. Okay. Last Yi Zeschua.
Hi, Doctor. I think the objective function is to reduce the cost for the exchanger capital cost and also the water for it. Yeah.
Yeah. Okay. Right. So basically, based on the data that we have, based on the data that we have the cost of water, which we don't know how much then the flow rate of the water is, but it for sure it costs money, and then we don't have the heat exchanger right now, which we want to design it. So and of course, designing the heat exchanger also costs money. So the objective function in this case is obviously we want to minimize the all of this costs together. So that's the objective function, and those costs, because we say we want to minimize the cost, and then that cost consists of the cost of water, the cooling water, and then cost of the capital cost of the exchanges. So these two costs. um, and then the equality constraints in this case, equality constraints that okay, now tell me what is then equality constraints in this regards. um yeah, okay, then Daniel again. What is an example of equality constraints that you think?
I think it's the can be the flow rate
That flow rate
of the
equals to.
water, and maybe the heat capacity.
Yeah, so it's roughly the energy balance around around the exchanger, because one thing we need to know is that how much is that heat that we are going to transfer from the process stream to the cooling water, basically, right? So that's how much energy that we want to transfer from the process stream to the cooling water. So from this guy to the other guy. So that's one equation, which is then the controlled or yeah, influenced by the heat transfer coefficient in the heat exchanger itself. And then how much is then the heat that is being transferred over here, which is then the Q. Well, we know that the temperature in is then 170, temperature out is 80 degrees C, and we have the flow rate and we have the CP. So the how much then the heat needs to be transferred is very easy. So it's that Q equals to mCp delta T. So that's the first equality constraints that we can think of. And then the second equality constraint is that if this is then the amount of heat that being transferred, how big is the exchanger? So this guy will be equals to that UA delta T LMTD. So that from that UA delta T LMTD, we can then know how big is the exchanger. So in this case, we have at least two equality constraints, and then once we know the other another question is that we need to know the temperature outlet of the water, so we can then use the same equations of mCp delta T for the water. so that we can then know using the same Q, right? That's the same Q that is being transferred from the hot stream to the cold stream, and then that cold stream will increase its temperature by a certain degree, which we can calculate as well. So we have three equations on the equality constraints, and then you can also say, well, T minimum here, I put this T minimum as an assumption equals to 10 degrees C, and this T minimum is do I not put it here? Yeah, it's basically this T minimum is then the minimum temperature between it's counter current, right? So it's counter current, so one goes this way and the other one goes that way. So the difference between this and that, I mean, this cannot be 10, I mean, assume. So it's like a 10 degrees C over here because we have inlet and outlet. So we have a 170 over here, and this is then 80 degrees C, and then this is then 25 degrees C, right? So okay, so this is not valid. So this that 10 degrees C is then 170 to here, so it has to be minimum or larger minimum. See? So minimum of 10 degrees C. So you can have like a 160 degrees C, 150 degrees C, and so on and so forth at the outlet of the cooling water. But you cannot go like above 160 degrees C because we have these constraints larger than or equal to. So that's another inequality constraints that we can see from this problem. And then what are the variables? What are the variables? Variables. So variables in this case is something that we want to find out. Something that we want to find out. It is not known, but we want to find that out. So that's the decision variable or the independent variable. So in this case, you could then think of from this example, right? We know that minimum delta T min is about 10 degrees C. So you could also say, well, what if I do it this way? So if this is then 160 degrees C, this could be 150 degrees C, right? So the outlet temperature of this guy can be like another variable, which in this case a variable that we need to know. The easiest way to see is that also like this one. Well, anything that has question marks, like in this case. So A is then a variable that we don't know. Q is also basically a variable which we can calculate. Like you know this already, we can calculate that, but it's unknown at this point in time. Parameters is information that we know. Yeah, it's this inlet temperature is the parameters. These all parameters. This parameter. All of these numbers that we know. It's what we call parameters. This overall heat transfer coefficient is also a parameters. But suppose we have made the model and then we try to solve this and we get a number, and then we could then use the same model by, and then we try to solve it by changing the one of the parameters or some of the parameters. For example, if I solve it like what if the overall heat transfer coefficient becomes 1100, what would be the value of the objective functions? Or if we can say, okay, now I make a mistake, so this could be like 200 degrees C. So if it's 200 degrees C, what would be the optimum or the minimum cost that we can get? So using the same model that we are now developing, we can then play around by changing all of the parameters which we know as sensitivity analysis. Yeah, because all of these numbers, they may not be as accurate as this is. Yeah, practically speaking, they will change. They will change. Yeah, I put it here. So objective functions, capital cost and then operational cost, and then equality constraints, the three energy balance equations. The inequality constraints, yeah, we have the delta T larger than or equals to 10, and then obviously the flow rate, temperature outlet, and an area of the exchanger, they all have to be like a continuous variable positive. Yeah, it has to be like a real variable, real positive variables. It cannot be like a negative. It cannot be like a negative. But it can be continuous. I don't see any necessity for that to be like an integer. So problems like I put over here. So apply suitable. Once we know this five. Once we get till this 0.5, we know already. Like in this case, this is then 0.5. Yeah. So all of this is then how to call it, the up until point 1 till point 5. So we have the whole formulations over here, and then we can see that the objective function has this exponential factor into it on the variable, because a is a variable. So that makes this problem non-linear. The objective function is non-linear, and then the constraints in this case is non-linear. So because if either the objective function or the equality constraints are non-linear, one of the constraints is non-linear, and then the problem would be non-linear as overall. But if everything, like this objective function and all the constraints, they are all linear, that becomes the linear programming problem. Okay, and then if we have like an integer, it will become like, if it's the integer is combined with linear problem, we'll have like a mixed integer linear programming. If it's non-linear and then we have the integer, we'll see mixed integer non-linear programming, which is the most difficult problem to solve. Think yeah, degree of freedom, you know that optimization has to be like larger or equals to 1. Yeah. Nah, basically, I will look into this. Do you have any questions? So at 3 o'clock, I will go to the second part of the optimization class. Do you have any questions so far? Any question? No. Okay. If there's no question, so what I want to share here is quickly like a basis optimization. We in the first part we know already on how to formulate the problem, how to formulate them in a mathematical sense, and then we can then identify whether that problem is a linear problem or non-linear problem, or if it's like an integer linear non-linear problem. Yeah, quickly, very quickly. So now in this case, we will then see what actually is, once we know the formulations, we will need a solver. Yeah, we'll need a solver. So we need to make a formulation. Number one, understand the problem and then make a formulation. And then once we get the formulations, we see whether this can be whether this formulation is linear or non-linear. I will have to draw it. I think I will draw this for you so that you can see this. So number one is that make the formulate the math, and then once you see if it is like if it is LP, NLP, integer LP, integer non-LP. So this is the easiest problem to solve. Easiest. This is not so easy. This is depending on the size, the integer, depending on the size of the problem, it can be easy or it can be it's not that easy, but it just like takes more time to solve the integer because of its combinatorial problem, and this is then the most difficult one to solve. Okay, so for each of these problem, we have a specific solver for that solver to solve with. So solver A, solver B, solver C, solver D, and so on and so forth. So it's for example, yeah. So once we formulate the math problem, we know what type of problem that we are dealing with, and then we can then choose which solver which is more suitable for our problem. Okay, so these three aspects. So number one, again, formulate the problem. Number two, evaluate the problem whether it is linear, non-linear, and so on and so forth. And then number three is then to select the solver to solve the problem. Okay, so three aspects. Yeah, that solver basically, so optimization and solver, they go hand in hand. So if you can imagine, if you can then close your eyes now, you don't sleep, but just imagine with me what the solver does is basically, and then how it gets things rounded. It's basically imagine that you are like a blind person. right? And then you can I draw? I think I can draw here, right? But it's just going to be quite complicated. So what we want to find is basically this peak, right? The in optimization, this is then the maximum profit, so to say, right? Because this is then the highest. So this is the maximum profit. So imagine now your problem has like it is like a 3D problem. So you have the x-axis, you have this x-axis, you have x-axis, you have y-axis, and then you have the z-axis, which is then your objective functions. Yeah, this is objective functions, and this is your variable one. This is variable two. Okay, your variable one, which is to the right. To the right is then your variable one. Into the screen is then your variable two, and then this height is then your objective functions, which is the z, and this is then your optimum value, and then you are. No, I don't like this. Um, and then you are simply like a blind person, and then this blind person, it doesn't know, right? It doesn't know whether, or it cannot see this. It cannot see this point. So these algorithms or solvers, they simply not us, right? So, I mean, it doesn't know whether this is the highest peak or not, but it knows it has two capability. Number one, it knows where it goes up or down. Yeah, kebetulan. So we'll just start from here. So this solver is just like this blind man at the valley somewhere here. So it wants to get to this guy, to these positions. It's a blind person. So how do you think it will get there? If it's a blind person, it doesn't know where to go, but it has two skills. The first skills is that it knows where it goes up or go down. So if we move it here from here to there, it knows where if it is going up or going down, it knows it. Yeah, either it goes up or not down. That's the first skill. And the second skill is that it can not only step forward or step backward, it can also like jump to here. It can jump as much as possible or as far as possible, to the right, to the left, wherever you want, 360 degrees C, sorry, 60 degrees C in 360 degree. And then it knows whether this position is higher or lower than the previous position. That's this on these two skills. Okay, so this is then the in a nutshell, in a very pragmatic language, what the solver is all about. Yeah, and then all of those solvers that you find, what is different, I mean, what makes them different is that how it gets from one point to the other point, and then how to make this jump more efficient. So that's basically what it is. Yeah, if you move one step to the other step, that's basically what's in the algorithm, and then how it moves around it. So for example, if this is then a blind man, you could see. So now you want to jump from here. I mean, you move from here to there, to the right, and then to the right, and then to the right, and then to the right, right? And then you can see up until here, it's clouded, and it gets lost. It gets lost. So that's number one. And then with another solver, you could also see, well, I'm not going to move to the right. I'm moving that way. So it knows, okay, now it's over here. Well, it feels the same, but it's slightly higher, and it goes further to here, and it goes further to there, and it goes further to here. And then in this case, well, we can say I also want to go further and further and further and further and further and further up until here, right? And then it cannot go further, because the further it goes, it will then move, it will then drop down, right? So it knows that it's not going up, it's going down. So once it's going down, it says, okay, now I have to stop, I have to go back to my previous locations. And then it will then say, this is then my optimum. Yeah, because simply it doesn't know. If it goes to the left, it will find the higher point, but it simply doesn't know. It's just following this trajectory, So that's a type of solver as well. And another one is also like, for example, you are here, and then you jump straight into this into this valley, and you die. Right? So and then you die. die. So that solver can also stuck here into this valley. It cannot go up, it cannot go down because it's simply stuck. And then what you could do is then okay, let's reset this, put this. It will then start from here. We will start with a new initial point, initial point, and then we can then go up and so on and so forth. In all of this solver, so one solver can end up over here, it can also end up over there, it can also end up over here, it can also stuck in the valley somewhere without being able to escape. So you get the point, yeah. So because for all of these problem, that LP, NLP, and so on and so forth, the solver can may or may not be, especially for the nonlinear one, may or may not be able to solve for the what we call like a global optimum. Like in this case, this is then the global maximum. This one is more like a local maximum. Yeah. I will skip everything here because I think you know this already. I will skip this, skip that. So there are two. There are what I want to say here. So there are yeah. Basically this is a simplified one, yeah. This is for I'll just go through this very simple one. So we formulate the problem and then we see whether there are more than one variables to solve, or maybe if it's one variables, so this is not really practical. So if it's like more than one variables, I think this is not so correct. But any case, so if we have like a variables and then if the function can be derived, yeah, if the function can be derived, for example, if you have like this kind of like functions, you can derive this, yeah? You can derive this. If the function can be derived mathematically, we typically use like a Newton or quasi-Newton method. And then, well, the derivation itself is behind the scene. Yeah, we may or may not know this, whether we can derive it or not, but we can always try. So if we can try, if a certain software has this capability, we can just use the solver, try to see if it can solve the problem. If it cannot solve the problems, even after you change the initial points, you can then try to what we call like a function value method. So we don't derive the problem. It's just that they use different values, different sets of independent variables in such a way it will then calculate the respective dependent variable and then just simply compare it. So what I mean by that, if just to make you yeah, this just to recap because you know this already. So if we imagine that we have like a 2D problem, yeah, we have 2D problem. This is then your independent variable, this is then your dependent variable, the f. So basically you have like this kind of graph, and this is what you want to maximize. This is then your objective function. And then you have like, for example, this is then your starting point. So x0, and this x0 from the equations you can put that in, right? So for example, this case you have a reactor, and then you have I don't know, a temperature. Sorry, you have a heater, right? So you have a heater, so you have a, and then this temperature controls the yield of the catalytic system in this, and then you can then get your yield, for example, and this yield is in this case is then your f. So is then your f, and then this temperature is then your x. Yeah, to simplify the problem. So you know, from your experience, you know that it's if you change the temperature, your yield will change. But you don't know what this function is. You don't know f equals to blah 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 x. This one's something that we don't know. Yeah, this is something that we don't know. Sorry, something that we don't know. Yeah, we don't know this. But you have this in the lab or whatnot. So what you could do is that okay, now if I put like this temperature of like 100 degrees C, which is this, and then you can then monitor what is then the F. So you have maybe, for example, I don't know, 0.6. And then okay, now if I put like this x is then the x1 is the 150 degrees C, and then goes something somewhere there. And then so it's maybe 0.8. And then if you move like 50 more 200, and then you get like something like this, 0.7. And then right, so it's 0.6, 0.7, and then 0.6, 0.8, 0.7, and then somewhere in between, in this from 100 degrees C to 200 degrees C, there is a maximum point somewhere. Is it the 0.8? It's something that we don't know. Yeah, so that means we will then try to find somewhere here. So make another one over here, 130 degrees C, and then maybe this one is then 170 degrees C, and then you can then try to see, make some experiments, try to see if the objective function is increasing or decreasing. So it's something that you can play around. So the point is that playing around with the set of the independent variables, yeah, you change them. That is what we call the function value. The phrase, yeah, you don't have to memorize this, but then it doesn't use the way it solves the problem. It doesn't use any derivative. It's just like changing the set of independent variables in such a way that they can find the optimum value over here. So value over here. How they change it, like for example, from your initial point from 100 degrees C to 150 degrees C, how they change this is then the algorithms behind the solver. So different solver will give you a different step function, either to the right or to the left, or how far. So that depends on the solver. So please be careful on the type of solver that you're going to use. So that's basically in a nutshell this guy, derivative. I think all of this you can read through. Yeah, you can read through this. So yeah, it's a very quick recap. And then I mentioned earlier that the linear problem is very easy to solve, right? Because of its nature. The question is that why is this very easy to solve, and then how do people solve that? We'll spend some time on this. And then simply because it's very easy to solve. So if you find yourself in a situation that you have to solve nonlinear or integer, try to reformulate the problem in such a way that it is as linear as possible. Yeah, just try to make them, if you cannot convert it directly to a linear problem, and then try to make it as linear as possible. Okay, so that's the practical side of this. Now, what people do in because of that simplicity, and then it's because we want to have solutions, right? We don't want to make formulations and we will not be able to solve it. We don't want to end up in that situation. So we want to be able to get the solution. So that's why we tend to simplify problems to make it as linear as possible, and then we can solve it, and then gives us like directions or decision making. So what is then linear programming or linear problem? So linear programming is because of the simplicity, it's widely used in the industries. It is we call it linear because the objective functions and everything, the constraints and stuff, they are all linear, hence it's a linear. Typical problems that we are solving with this linear programming is this production planning, the one that you saw already. The supply chain optimization that also saw already, and then another supply chain optimization. So all of this, the supply chain is very big as well. Yeah, I mean the problem is also very big, and then if we have like combinatorial problem, like the integer variables in it, it will become also very complicated to solve. But nonetheless, the bottom line is that they are all majority of them can be formulated in terms of like a linear problem. So let's see this guy. We have touched this, right? And then how do we formulate that? The same way that we formulate that heat exchanger that we saw already. The maximize the profit. Where's my pen? We want to maximize the profit, which is then the P profit or whatnot. So again, it's the same income. The product sales minus the raw material cost minus the processing cost. That's as simple as you can get. I mean, this is the only thing. And then this income is this guy, right? So this is then this income comes basically because we're going to we're going to sell the product, right? What we don't know is that how much is then the crude one, how much is crude one, how much is crude two. That's something that we don't know in barrel. We don't know. We don't know how much that we have to purchase, but we can then simply say, well, this is X1, for example, this is X2, yeah, as easy as that. And then from X1, we know that we can make this amount of gasoline, kerosene, and so on and so forth. And then with X2, we know that we can also make a different set of amount of gasoline, kerosene, and so on and so forth. And then these are the corresponding prices. So basically, we know that it's a 36, right? So 36 gasoline. So 36 times gasoline, and then this is then 36 is then dollar per barrel, right? Dollar per barrel. So dollar per barrel multiplied with barrel per day, it will then give you dollar per day, which is then this unit. So be careful of the unit, yeah. So 36 times gasoline plus 24 times kerosene plus 21 times fuel oil plus 10 times residual. So somehow residual has a price as well. That makes the income, which is this. So this one, you're good. So this is then the first H1, right? The first constraint, and this is equality constraint, as you saw. And then what is this guy then? This guy is a raw material cost, which is then the crude one times 24, because that's the price of crude one. So crude one 24 times X1, and then times crude one, and then 15 plus crude two. And then the processing cost also depending on the crude, so half of crude 1 plus 1 of 1 times crude 2. So that's the processing cost, which is this case. And then this is the generic formulation, but it's very long to write, right? So we typically use like symbols. So in this case, you have like so this one X1 and X2, this we call X3, X4, X5, and X6 somehow. That's why this symbol comes. X3, X4, X5, and 6, and then the raw material cost is then the 24 X1, 15 X2. The same thing. You just make it in symbols, and then the profit is that you can then simply put this in 36 X3 and so on and so forth, and then minus this one. So this minus this guy, and then minus that guy. So you have this kind of equations. Okay, with me so far? I hope you're with me so far. And then we know that the equality constraints, yeah. So the amount of gasoline that you can make is basically if you put X1, if you put crude one, you will get like a 0.8, yeah, 0.8. This 80% volume percent. So 0.8. So if you have like X1, it will be then the gasoline is then 0.8 of X1. If you have X2, crude 2, you will have that 0.44 of gasoline. And then you sum 0.8 x1 plus 0.44 x2, you will get the total gasoline. Yeah, the total gasoline over here, total gasoline. So if, for example, we don't use x2, we don't use crude 2, so that means the amount of gasoline is left with 0.8 of crude 1. And then the other way around, if we don't use crude 1, that means we are only producing gasoline using crude 2. So it's the amount of gasoline produced is then 0.44 x2. That is as simple as that. And then we do the same for the kerosene, fuel oil, and diesel using this table, basically using this table. And then the inequality constraints. We know that gasoline maximum is 24,000, right? Gasoline 24,000, kerosene 2,000, 6,000. So this is then X3, X4, X5. So X3 is then less than 24,000, and then we know that X3 is basically this. So we can just simply put these equations in here. So you will get that guy. So 0.8 x1 plus 0.44 x2 has to be less than or equal to 24,000. We do the same for the kerosene and fuels. Okay, and then all of these variables x1, x2, x3, and so on and so forth, all of these crude flow rates, they have to be positive for obvious reason, right? You will not see minus 10 barrels per day. So with this, so we have the full version of the optimization formulation. So basically, this guy is in the full versions. So we have x1 until x6, right? And then we can also have the simplified version. So that simplified version is that if we so you put everything into x1 and x2 like this, guys, x1 and x2, yeah, as the constraints, and then you know as well from the objective functions you have x3, x4, x5, and so on and so forth, and then we know the correlation between x3, x4, x5, and x6 against to x1 and x2 using this. So x3 is this guy, so you put this back into the objective functions in here in this case. Yeah, so you replace x3 with x1, x2, x4 with x7, x2, also replace x5, replace x6 with x1, x2, and you will end up with the simplified version, which is 8.1 x1 plus 10.8 x2, and then this is then the constraints in terms of x1 and x2. And in this case, we no longer have x3, x4, and x5. It's all only x1 and x2. And then this crude, both of the crudes, they have to be positive. Any questions on this? Question on this? No? So we will use these simplified versions to help us understand how the linear problem works, how the linear programming works. Yeah, and then if you go to textbooks as well, this is how they start explaining the linear programming problem. We use this simply because we only have two variables to solve, right? Two variables to solve, and that makes it like a 3D problem. So we have x1, x2, and then we have the p, so the three-dimensional problem. And then in this case, we can simply draw it on like a 2D plane, like in this case, like a graphical. So so we have x1, which is then crude 1, and then x2, which is then crude 2, yeah, in thousands. So in this case, the first constraint, which is this one, 0.8 x1, 0.44 x2, less than or equal to 24,000, which is this, the blue constraint, which is this line. And then the orange constraint is then the second, that line, and then the gray constraint is this line. So and then we know that x1 has to be like a positive, x2 has to be like a positive, and then we can see these parts. Oh yeah, it's not really that this one, that one, this one. This is your search space. This is the search space. Can you follow? Yeah. So and this with this graphical solutions, we then in this case we have to then put this point. This is then the objective functions. Yeah. 8.1, 8 x1, 10 x2. This is the objective functions, and then if you put it here, it will be something like this. Yeah. Make sure that it's 8 and then 10. So 8 and then 10. Something like this. Okay. Something like this. So and then we want to maximize it. So if obviously if you have like x1 equals to 0, x2 equals to 0, and then this p becomes 0, 0, 0. So if you want to maximize it, it has to go as far as possible from the point of 0, 0 to that positions. So if you move it over there, and then you will see eventually you will then end up in this point number 3. Draw it very I draw it very ugly, and the rest I think you can follow me. Hopefully you can follow me. So This point 3 is basically the solutions to this problem. So in this case, we can see this is then the amount of x1. This is then the amount of x2. Okay. I put here also the, if you say, for example, this is an 180,000. If the x1 equals to 0 and then the x2 is somewhere in this point, this is also another point over there, point 2, which is 25.6. This point 3 to 88.6, and then this is then point 4, which then 24.3. Okay. So that's how we solve this in graphical manner. But then some very smart people, they developed the like the algorithm, so we don't have to for bigger problems more than 2x, we will not be able to solve this graphically, so we have to use some kind of programming. So then they come up with what they call like a simplex method by Robert Danzig. Just Google this name later on. So I want to skip how this is done. I want to skip it, but we will. I'm not really sure if we can find some time. I have the I have some a video to show you how that works, but I'm not really sure if we have some time for that. You can watch this video later on, in your own time. How it works. What I want to show you is that later on I'll show you. I'll show you how it works. But then let's try to solve this problem in Excel. Yeah. If you can, I'll show you how to solve this in Excel. If you can then open your Excel. If you can open your Excel. And then you have, like, for example, let me see. So for those of you, if you don't know, if you don't know how to use Excel solver, we'll see and try to do this together, so that you know. Wait, what is it again? Simplified version, so that you can have a feeling, and then later on with more difficult problems, then you can do it on your own. Maybe I'm too quick. So anybody, can I confirm that all of you know how to use Excel solver, so that I can skip this exercise? If not, then I will have to do this. Do you, each of you know how to use Excel solver?
Yes, we learned it in the optimization subject already.
Okay, so shall I skip this, or
I'm not yet taken the optimization, Doctor, so I
okay,
don't.
okay, so you need to, okay, let's okay, let's do this. If what's the name again? Sorry. Zul Hafiz. So okay, so some of you don't take the optimization because it's very strange. I thought this should be like a your. Anyhow, I don't know how it works now. Optimization course should be like a prerequisite for this course. But in any case, we have x1, right? And then we have x2, which we don't know, right? So I just put it here, 1 or anything else, any number, and then your objective function is that one. So we have like 8.1 times 1 plus 10.8 times x2, right? So basically this is then the objective function, which is then the USD dollar per day, right? And this then barrel per day. Yeah, these are objective functions, and then we have constraints, right? So we have constraints. So the first constraint is that constraint number 1. So it says that it has to be lower than or equal to 24,000. right? And this is then 0.8, okay, 0.8 times x1 plus 0.44 times x2, right? So it has to be lower than 24,000, which is in this case, if you put 1 barrel per day each, it's obviously it's 1.24. And then because you add 0.8 plus 0.44, yeah, it is then 1.24. Yeah, if you put like this 0, you get that only x2, and if you put this one and then the other one is 0, you get that 0.8. And then if we don't know, just put 1. That means we're not making any profit. So that's basically what this is. And then the constraint 2, we have this equals to, and then this then 2000, and then the constraint 3, this is then less than or equal to 6000. Okay, just to make it clear, 0.05 times x1, 0.1 times x2, right? And this is then 0.1 times 1. Okay, so just put this some number. Okay, so basically we want to maximize this object. So far it is clear, yeah? If not, let me know. Okay, if not, let me know. So basically we want to maximize this, to this guy, to maximize. Okay, so we go to data, and then we have the solver over here. If some cases you don't have the solver, you go to file, and then I think option, file option, and then now let me think. In general, let me think. Add-ins. Sorry, add-ins. You go to add-ins. Okay, you go to add-ins and then add Excel add-ins. Yeah, options, add-ins, and then Excel add-ins, and then click go, and you have the solver add-in. So tick this, because now I tick this already. So you tick this, and then you click OK, and then it will give you the solver. So that's solver. Okay, so that's solver. So basically, Excel has three types of solver. The first one is what they call like a GRG, non-linear. So it puts non-linear here already. In the optimization course, you will learn about what this GRG means. Yeah, you will learn about that. It is non-linear. This is to help common people to know that this is a solver that we are going to use should we encounter any non-linear problem. And then we have Simplex LP. So it's based on that Simplex approach, and then it solve. We use it to solve linear problem. Yeah, to solve linear problem. And then evolutionary is what they call it use like this genetic algorithm. So remember that that poor guy who what is that guy? That poor guy who trapped in the valley. So this guy. So if you use like a traditional this GRG on the linear, well, conceptually, once it's stuck in the valley, it cannot go up. Yeah, it's just stuck. So this linear, the stochastic optimization using that evolutionary algorithm, it can then somehow like a reset. So it doesn't use any it doesn't go here, there, or here. So it uses this random number where this guy can just simply disappear and then somehow appear over there. Yeah, there is an algorithm between the genetic. The algorithm is there, so in such a way that it doesn't use any derivative. So anybody who is stuck in the valley or is stuck in the problem, it can then come up at another point and then restart the optimization journey, so to say. So this evolutionary algorithm, it can help you if you're stuck with a kind of a problem. Yeah, but that doesn't mean that it will solve all kinds of problems necessarily. Just like you have to be careful with that. Yeah. So we know that this is linear problem simply because, well, the objective function is linear and then the constraints, they are all linear. So this is linear problem. So that means we'll then have to switch this to simplex LP. Okay, this is the method. Well, I shouldn't do this first. I have to show. So objective function. So what is then the objective function, which is this one? Yeah, d4 is the objective functions. So what do we want to do? Do we want to maximize it, minimize it, or set it to a certain value? We want to, in this case, maximize it. Yeah. Okay. So we want to maximize it. We want to maximize this. And then what do we want to change? So this changing variable cells is then the independent variable or the decision variable. So in this case is it is x1 and x2, right? X1 and x2. And then what are the constraints? So in this case we have three constraints. You can add. So you can also say you can do it manually, yeah, one by one. So this one is less than the other one. You could do so like this. So b6 less than d6, and then you can do you can add more. So this one less than that one, add this one less than this one. You can you can do so, right? Something like this. So you can do it, or you can then because we have put this so nicely to each other. You could also do something like I think you could do this. Could do it like that, less than like that. Okay, see, you could do it the same way because you put it already on next to each other, so you can combine them all. And then we know that x1 and x2 are positive variables. So in this case, it's tick automatically by default. Unconstrained variables non-negative, but you could also say something like this. So this one has to be bigger than or equal to 0. Yeah? And then you have many options as well. Yeah, equals to integer, binary. This one I don't know. But nonetheless you have this. So we have the decision variables to be always positive, which is this is basically what it is, and then all of these constraints are less than the right hand side part of the constraints. Okay, so we have specified the objective functions. We know that we want to maximize it, and then we know these are the variables that we want to change, and then these are the constraints that we have defined, and then we have selected the simplex, in this case the tool, because we know that this particular problem is a linear problem. So and then we can then click solve. So I click solve. Yeah, you want to keep, yes, click keep, and then click OK. Yeah, you can later on, I think you can go to this reports later to see, but I'm not going to go through that now. Click OK, and then you can see the objective function is that 286758, which is where was it? Which is this? Yeah. 286758 is then the objective function, and x1 is then 26206, and then x2 is then the 6896 barrels per day. So so both using this graphical and then the solver, we can achieve the same solution. Okay. So how it works, basically, I will spend some time to understand this. Can you see this? Just to give you an idea, yeah. Just to give you an idea. I don't know why it comes. No. I hope you can see this, yeah. Just to give you an idea. So I put this simple examples already. How this, I mean, how it works. So we have like one constraint. This is 1. This is 2. And this is 3. So we have 3 constraints, and then that makes that this part is then this is then the search space, the feasible region, So the objective is then to find the objective to evaluate these objective functions to x1 plus x2, and then we know that it's f equals to 1. This is then basically the minimum value, which is then point B. So x1 equals to 0, x2 is 1, so this is then the minimum value. And then we know that at this point D, this is then the maximum value. So we know this already. So and then you can also see what values are in between. So you could also calculate that. But then these extremes are the important values at the moment. So what this simplex programming does is that it moves from 0 0. In this case, this 0 0 is the invisible region. So it will then try to move through the edges. Yeah. What edges means is this one. This is one edge. This is another edge. This is another edge. So all of these boundaries, what they call edges. So you will watch this. If you watch this, and then you will then know how I'm doing this. So it will then first move from the 0 0, like I mentioned. You want to maximize it, yeah. You want to maximize it. So from 0 0, it moves to this point B, and we know for sure, yeah, this is then maximum. This is then minimum, yeah. This one. So this is then minimum, point B is minimum, point D is maximum. And then for maximizing, that means we have to move from 0 0 to point D. Yeah, we have to move from 0 0 to point D. That's the idea, because we want to maximize it. So it moves from 0 0 to point B, right? And then it moves as well to point C. See, from point B it moves to point C, and then it moves to more to point D. And then by the time it reaches point D, it knows already that this is then the maximum value. Yeah. Why it knows it, and then you have to watch that video. And then if you want to minimize it, that means it's just point B, right? So there, point B, the same step, same path it follows. So just point B, and then it just stops there. So we know. So basically, the idea of this simplex is then it will then move from the edges. It will evaluate the values at the corner over here. It will evaluate here, it will evaluate over there, it will evaluate over here, it will evaluate over there, in such a way that one of these is then the maximum point or minimum point, depending on what the question is. Okay, so that's how this simplex method works basically. So if I solve the same problem using that graph, so it starts with this 0 0, and then we know, what is it? Where's my so we know that this is then the this part. So this area is then our search space. Yeah, we know that. It then goes up to point F1, and then it goes here, and then it goes to the point F3. So that's, and then it will then stop. It will stop at point F3. Because point F3 is then the maximum value. It will stop there, and then it gives you the results using this simplex algorithm. And then we can do that quickly in Excel solver, like I showed you already. But just to give you an idea how this particular solver works behind the scene. Sensitivity analysis, I think I will skip this. You have to read this on your own. This is then the results. This is then the results from the Excel, yeah. Basically. Okay. So I've covered, at least in less than 2 hours, some basic go through on the optimization. So bottom line is that we understand what the problem really is, and then we formulate the problems as we saw already with the heat exchanger and then the refinery modeling. And then yeah, we have done this exercise. So I hope that at home that you will do the other examples that we have already in the slides. And then we formulate that, and then we evaluate whether it is linear, non-linear, and so on and so forth. And then we can use Excel if we have decision variables of less than 200 variables. Yeah, if you have like decision variables of less than 200, you can use Excel solver to solve your problem. If it's more than 200 variables that you want to find, it's Excel solver is not for you. You have to use a different software for that. And then in the Excel, you know, you have GRG to solve nonlinear, and then the what was it again? The Simplex for linear, and then evolutionary algorithm for the for any other things that you cannot solve with these two. Do you have any questions? I think we will have a break, like I don't know, 5 minutes or so, so that you can get some fresh air. And then because I want to explain to you, we miss something like last week, to emphasize it a bit, and then to get to make you familiar with this solver again. Any question? Is there any question? No? Well, if you don't have any questions, and then we'll break for 5 minutes, yeah. So let's make it like 8 minutes or so. I will be here, so if you want to go go to I don't know, whatever you want to do. In 7 minutes, so 3:55, we will come back here and we'll continue. But if you have any question, you can just ask me during this break. Otherwise, I will then touch this refinery optimization, refinery introduction again, in 3:55 at 3:55.
Hi, doctor.
Yeah,
I got one question, but not related to the topic.
fine. Fine.
For the simulation software to access the UTP PC one, right?
Yeah.
I already gain access for the VPN, but
Uh-huh.
how to access to the symmetry?
Share me your screen.
Share my screen. Hold on.
Mhm.
About the VPN or what?
Well, correct me if I'm wrong. You said that you are connected to UTP VPN, right?
Yes, I already downloaded the VPN, but I'm not sure where to go to access to the symmetry software.
So that means you are now, if you are connected to UTP VPN, that means you are now seeing UTP computer. No?
No.
Okay. Why not? um. Uh. Yeah. Um. Um. If you don't, if you are connected to UTP VPN and then you're not looking at UTP computer, that means you have to talk to our IT Cik Nizam. I think Afiq or Chong Yang can help you with that. So talk to Cik Nizam, and then how you can see the computer of UTP. Because once you see the computer of UTP, you can then simply search. You can simply search like a symmetry, for example, symmetry, and then you will get your symmetry software, which you can then click and then open it. But if you don't see UTP computer, means that one I cannot help you. Yeah. Afiq or Chong Yang, I think you have to help the students so that they can use the symmetry. Yeah.
Yes, yes. Later, I think we have to solve this during the weekday because Cik Nizam is not available during the weekend, right? So maybe we find a time in weekday. Yeah, we make an
Yeah.
effort.
But
I am
make sure that you get access to the symmetry. Yeah.
I am very a bit confused because I connected to the VPN.
Okay.
Then how actually should it be done? The
Oh,
Mm,
UTP PC.
yeah, right. One you first VPN, and then there's server. You have to connect to the server. Only then you can open the VPN. Which you will see the monitor of the screen, and then you see
Oh, I see.
the.
Can I know where can I get the link to the server?
Uh, okay, I'll take a look again on this. I'll let you know the name later. Okay.
Oh, okay, okay.
We
Thank you, thank you,
communicate in WhatsApp. Yeah.
thank you, thank you.
Right.
in that VPN connections. So you go there are 5 steps, I guess. 5 steps. Remote desktop. Yeah, I mean because I don't have UTP email, so I don't know how to show you. I cannot connect to UTP, yeah. But then if you follow this, there are 2 points, right? I mean the point A, section A and section B, because you are accessing it from outside of UTP. So section A and section B you have to fill in. How far are you with the section A and section B in the procedure?
Oh, I see, I see. I just completed the section A. I will try the section B, I think.
Yeah. So because
Okay.
if you the first page, yeah, number one, complete section A and B if you are accessing this from outside UTP. So so you've done A and then you still have to do B. All right, and then there are step 1, 2, 3, 4, 5. At step 5 in section B, you should be able to connect to a virtual PC of UTP, and then you will see the desktop of UTP computer. That's what I meant.
Yeah. Number 5 to right, we can see the screen now, the monitor.
That UTP library.
Okay, I will try again.
Please do so, yeah. And then please keep us updated so that we know. Okay. How familiar you guys are with process simulation software? Because I need to ask this. So I will need to know whether I have to spend more or less time in this. How familiar? So if I ask you right now to model a plant, can you do so or can you not do so? Like if I ask you to model like a refrigeration system, yeah, very simple one. If you ask you to model a refrigeration system, can you do it or no?
Hi, I'm Chua here. I'm not familiar with the process simulation software.
Okay.
Never do before.
Okay. No. Okay. Okay. So yeah. Okay. Good.
Does symmetry similar to icon or HYSYS?
Yeah, symmetry is the same. Symmetry is basically its icon. Or icon is symmetry. Um, um, and then if you know how to use HYSYS or Unisim or Petrosim, you know how to use symmetry basically. They use the same calculation procedures. It's just that symmetry is using Visio, so that the visual is a bit, yeah. I mean, from drawing perspective, it's a much bit more beautiful. Um, okay, let's continue. Um, any questions on this optimization? I went through this very quickly because my assumption is that you should have got optimization course before this refinery optimization, because it's a refine optimization, right? I mean, so that means we have to know refinery and optimization we can before we can do any refine optimization basically, by definition. But nonetheless, in the refinery we missed something. We have still 1 hour to go. Yeah, refinery. Uh, yeah. Now we have some time. Luckily, we have 3 hours now. What we missed, I think I've introduced you to some of this thingy. You can read, you can go through these slides or the references, books or literatures that I put, and then you can glance through it. Yeah, I know it's a lot of information, but if you can find some time, just go through it, and then you have any question, just like I mentioned in our WhatsApp group, you can just ask me questions, any questions, and then I may or may not be able to answer, but nonetheless. What I want to share is the refining stream characterizations. So there are two aspects to it. There are two approaches, like a traditional approach and then the more advanced approach. A traditional approach is more like we because we know that refineries, it has many components in it, right? So as we know already. So there are many components in it, and then like hundreds or maybe thousands of components, and then it's impossible for us to model each and every of those thousands of components. So traditionally speaking, people are then lumping these components together. So if we have like if there are components, they are similar in size, similar in chemical properties, they will just simply lump them together. So in such a way that become like a group, like the easiest group is then the piona. Yeah, it's the easiest group, the piona. So we have paraffin, isoparaffin, olefin, naphthic, and aromatic. So that's five groups only. So that's the easiest one. And then if we are talking about, like for example, the like an FCC, I will just go FCC or hydrocracking. Let's take an example. What is that? Hydrocracking, for example. So so this hydrocracking, fine. So you have one feed. Yeah, it can be like a gas well or whatnot. You put it into like this hydrocracking, so you have black box or something.
Doctor, will you share your screen?
Oh, I'm not sharing my screen. Okay. Um, yeah, share my screen. Okay. Um, can you see now? So where was I? Okay, this is like one stage of hydrocracking, so one stage of hydrocracking process, and we have like a feed of I don't know, gas wheel or something, and then you put it into like this hydrocracking units, and then this hydrocracking unit typically, like I mentioned, it's we have a reactor and we have a distillation column at least, and then everything around it. And then from this unit, if you draw like a black box like this, so black box like this, you don't see this, you don't see this. So you will then see, okay, what's coming in is then the hydrogen makeup, and then the feed, fresh feed, and then you have several outlets. The first one is then the gas, and then light naphtha, heavy naphtha, or if you want to combine it into naphtha, that's also fine, and then jet fuel, kerosene, and then diesel, and then the heavies. Yeah, heavies. So you have one, two, three, four, five, six groups of products, or six products basically. And then in this case, they say, well, naphtha is simply like a naphtha, or light naphtha or heavy naphtha, and then jet fuel, diesel. So they don't really care into what is in the diesel or what is in the naphtha. It is like C8, how much is C8? And then is it like iso-octane, like C8, right? Octane. If it's iso-octane, how much is in the iso-octane? People don't really care. So we just need to know, okay, I have this naphtha or light naphtha. If I put this feed into the hydrocracking, and then from the data you will get your fractions of naphtha, and then fractions of jet fuel, diesel, and so on and so forth. So lumping all of these, right? So for example, you have now in this case you have fresh feed coming with hydrogen, and you will get all of these products, and then you try to model this, and then that's what we call like a lumping model. So we lump all the components in the light naphtha fractions into light naphtha basically. So we don't really care how many C's, how many what type of C is it, like how many paraffin, how much paraffin, how much isoparaffin, how much aromatic in this. We don't really care too much. What we want to know is then the yield of naphtha only. And then practically speaking, and then the properties, well, it should be like behave like naphtha. We don't model the properties, we simply model the yield. So that's where this lump model is mostly used. Yeah, mostly used. And then if we want to model the properties, for example, this light naphtha, what is then the rate vapor pressure, or what kind of I don't know, the octane number and so on and so forth, we will then need to dig deeper, and then we will then need to know what is then the chemical structure. And for that we will need to have like a more advanced analysis, which is the laboratory type of stuff. So we need to have like a chromatography analysis, piona analysis, and so on and so forth. So traditionally we have this traditional approach, which is the lumping, yeah. And then we use this, like I mentioned, we use this typically only for to model the reaction. So how much is then the yield of naphtha, jet fuel, and so on and so forth. While for the alternative, so if we have the samples and then we go to the lab, and then we can then quickly get as much information as possible in terms of the molecules of the feed, and then we can then make the model of the molecular, and then we can then model the properties of the product easily. So there are several approaches. So this is then the UMIS materials that I put. So they know at that time. So in 2002, UMIS mentioned about this PhD thesis, and then this another thesis, and then somewhere something about Shell global solution approach, and then ExxonMobil's approach. The legacy of this UMIS material that I'm now going to share with you, they only mention about the UMIS works, obviously. This is their work, but basically, yeah. So for example, in this case, we have like there's no C0. We have like a C1, C2, and so on and so forth until C12, for example. Yeah, this is then in the range of gasoline. Yeah, in the range of gasoline. Sorry, in the range of naphtha. And then from that naphtha we can make gasoline. So that's basically how the connection is. Why gasoline? Because we only need to, because doing this is very complicated. It takes effort, it takes money, it takes resources. And then what they do, well, we just start with the most valuable product at the time, also at the current time, which is basically gasoline, diesel, and jet fuel. So these three products, basically. So they make this matrix for gasoline, one naphtha in this case. So we have until C12, and then the C, they have like a kind of like a grouping. So this NP is the normal paraffin, isoparaffin, normal olefin, isoolefin, normal 5, normal pentane, normal hexane, and so on and so forth. Okay, and so on and so forth. And then I don't know what this SI is. This one I don't know. And then this one maybe two aromatics and then two naphtanes. Yeah, 2A, 2A, 2N. That's what I think it is. So for example, in this case, we have like so all the C3 is over here, for example. So this represents the carbon numbers. So it's carbon number 3. So all materials or molecules, they are located in this. They are all C3. But then they also like if we know that C3 is the normal paraffin, that means this over here. Is there any isoparaffin for C3? No, it's very simple organic chemistry question. Guys, just to check if you are awake. Yeah? Is there any isoparaffin in C3? Anybody? Okay, I'll give it. I'll give that as a homework. Yeah. Find the answer if there is any isoparaffin for C3. Okay. Nonetheless. So if it's normal paraffin, that's C3. It's over here. So that's how they characterize the location. Oh, this S and N is the sulfur and nitrogen. So that's how they characterize the locations of the molecules. And then using this, so they know. So this one is another compound. That's another compound. That's another compound. That's another compound or group, whatnot. And then they then try to correlate this with the properties like this. properties of for gasoline, for example, octane number, viscosities, boiling points, refractive index, specific gravity, and so on and so forth. Yeah. So if they are here, what would be then the typical Ron number? What will be typical specific gravity, and so on and so forth. If it's over here, what is then typical of these properties? So they have huge database in it, so that they can then try to approach these molecular models in a bit more detail. A lumping model, yeah, it's just simply like a lump, like I mentioned to you already. So we lump this in terms of in reaction, like we discussed. So from that gas oil, we can make naphtha, gas, jet fuel, diesel, and then heavy, right? So it's we assume in this case, in this lumping, we assume that naphtha will behave all kinds of naphtha from C6 until C12. Yeah. We assume that they will all behave the same in terms of the reaction. Yeah, that kinetic will be the same, so that we lump it as a naphtha. So that's the first approach, and then the second one is then by distillation, for example, because when we separate that by distillations and then boiling point. So from a certain range, within this one range, we have like a naphtha fractions, we have the diesel fractions, we have the heavy fractions. Yeah, so that's how they try to approach this with the lumping model. And then yeah, depends on the what we want to measure, how adequate the measurements, and so on and so forth. We can then make this lumping model more detailed. For example, if you have we can lump this as naphtha, or we could also lump it like the light naphtha and heavy naphtha. That's the second approach. Yeah, naphtha number one. Number two is that light naphtha or heavy naphtha, and sorry, not light naphtha and heavy naphtha. And then the third one may be like, paraffin light naphtha and then isoparaffin light naphtha. You could do so. Yeah, depends on what you want to do. Depends on what you want to do. Okay. This is an example of the distillation column. I think we've seen this like last week, right? So this they lump it together. So they where's my pen? So they lump it. So this is then the residue lump. So this is all the residue. I'm moving from the right. So we have all of these gases, and then we have this I don't know something like naphtha, light naphtha, heavy naphtha, like a jet fuel, diesel, gas oil, residue, something like that. Yeah. So they really lump it. So if you go to like for example, this is then the CDU, and then we have this crude A, for example, crude A. They have this assay, this boiling point curve. So code A with this assay, they know how much is then the naphtha, and they know how much is then the diesel, and then they know how much is then the residue, for example. Yeah, so they can calculate that. We touched upon this like last week. And if they have like a different type of graph, for example, if they have this kind of graph, for example, and obviously they will then have more naphtha and then more diesel, for example. Yeah, and then very small amount of residue, for example, in this case. So this is then a lumping, one of the examples for the lumping. This is they get it into, I mean, it's basically the same. So for every of this lump, so this lump, so this volume, and then the true boiling point, and then they have, yeah, specific gravity, they have molecular fractions, they have molecular mass, temperature critical, pressure critical, all of this they make like a pseudo component. So in process simulation software, that's what they do in the distillation. So they try to lump it into several products, which gives us like yeah, roughly about the same critical temperature or critical pressure. So to be able to characterize the streams as much as possible. That's for the separation. And then for the reaction, there are two. Oh, well, there are two. There are several advancements. They started this in 1968. So we have feed, and then we have feed, and then we have K, and then we have the products. So this is basically the first approach. And then in this case, they assume always, I mean, because simply number one, we don't know. Number two, it's everything in nature is in many cases it works like a first order. Works like a first order. Okay, so this first order, whether you realize it or not, you have seen. If you don't know, yeah, you touch upon this during your reaction engineering or process control class. Control N. So we say if you have something like this, this is time, for example, and this is the concentrations of reactant, say for example A. So that you have a reaction A make into B, yeah, make from A to B. Just simply like this one, the one that we are now trying to discuss. So feed and then product and then A to B. So this is the first approach in say 70, so 68. And just to recap, yeah, because we will need this skill shortly. So typically it will the curve as we go along, yeah, we let this A reacts into B. As we go along, the concentrations of A will start at this point, so CA0, and it will then dropping down like this. So this is the first order, yeah. And then this graph is basically dc dt, dca dt, and then minus k, and then the ca. Okay, we say that this is first order because then ca to the power of 1, which is, well, basically first order. If it's a zero order, that means ca to the power of 0, that means only k. But typically these kind of reactions, they approach this in this first order because they have seen many of these data. So this is the first order, and then you can then how do you call it, integrate this in such a way that you have the dca and then this ca, right, and then minus k delta t, and you integrate this, integrate that, you will then see ln, yeah, ln ca0 minus k delta t, and you will have that ca equals to ca0 exponential of minus kt delta t. Okay, so this is then our first order equation. So if you put these numbers, if you put these equations into the graph, you will get this very graph. So this is what we call first order equation or graph, what you want to call it, up to you. So that's basically what this is. So they approach it in this manner, right? So that's this one. And then the next is that they have this 3-lamp model, and then they have this 4-lamp model. So they make it more and more complicated. Yeah, just to recap a little bit. So if you have something like this, so if you have like for example, so now you have like a plus b, and then this makes c. Yeah, this makes c. So what really happens is this in this case. So you have t, and you have c. So we recap a little bit on reaction engineering. So your A will behave something like this, yeah? And your B will start from 0 because there is no B in the beginning. So it will go up until like that, and then it will go down because it is consumed to C. Well, we make B from A, and then that B is then going to produce C, and your C will become something like this. Okay, so this is then the A, this is then the B, this is then the C. So this is then this whole thing. Okay, just to give you an idea on what we are talking about, because we're going to need this concept in a moment. Basically, how much? What time is it now? Right, so that's basically the lumping model, and then they make some experiments, either batch or continuous, up to yeah, I mean, they don't mention it, but then they then try to put, for example, in fit this is an FCC model. So they fit, so if you have like a gas oil, so they start with this guy, so they have this gas oil, they will then make gasoline, and they will then make coke and gas. So they don't care about the heavies like diesel and then jet fuel or whatnot. Why they care on this gasoline and coke gas? Because gasoline is then what they the main product they want to make this gasoline, and then coke and gas is something that, well, typically the gas they will then send it to chemical plants, and then coke is then the amount of, because it's how to call it, yeah. So it's a FCC unit, right? So you have the riser, and then you have the regenerator, and then among them there are two lines, and then the this riser, so the catalyst, it moves from here to there. So we have the reaction is only in this region, and then the catalyst is then being how to call it, becomes a place. I mean, the catalyst becomes the place, is the place to for the reactions, and then because you're cracking it. Yeah, remember, you're cracking it. It means you take you crack the component, and you also, with that, you take the hydrogen out. And then the more you do it, the more severe that you do it, the more carbon that you produce, which is coke in this case. And then that coke is then um, covering the surface of the catalyst, and it goes to the regenerator in such a way that that coke is then burned. That coke is then burned. So the coke is then, the catalyst is then now free of coke at higher temperature because it just burns, and then it will then send back to the riser, and then the cycle continues. Yeah, something like this. So this coke and then gas and then gasolines, I think that was then the reason why they chose these three items as the main products in their model, because of this information that this model can give. And then they separate this. Well, I want to know how much the coke, how much the gas, and how much the gasoline, not gasoline and gas plus coke. They don't want that. So and then the more, I mean, as you see, in the earlier year, the, well, not so much data maybe, and then the computing power is also not so much, and then they could only solve very simple problems. And then the more we go until this era, we can solve much more complicated problems because of the data, and because of also because of the computing power that we have. And this is the one that I mentioned. So the basic rate equation is simply how to call it, the first order. So we have K, and then we have the components here. So this can be anything. This can be like a gasoline, this can be diesel, can be anything. And then all of these are just some constants that they put to evaluate whatever they need to evaluate. For example, the activation function for heavy aromatic, activation functions because of these impurities, because of the metals impurities, the coking, and so on and so forth. So you can make these equations as fancy as you want to see, but then the bottom line is that this is a simple first order reaction. Yeah, first order reaction. How to do this? I'll give you an example, but before that, we will all finish with the model, the molecular modeling first, and then we come back to this. Yeah, see, mobile stand lump model, or they lump into like 10, how many components? 1, 2, 3, 4, 5, 6, 7, 8, 9, no, 10 components. Well, 10 lump model. So 10 components. So paraffin, naphthens, and so on and so forth. Yeah, this is what the approach is. And then they also have like okay, so that's it. So basically, so so they simply try to simplify the problem by lumping the components. Why they want to simplify the problems? So that they can apply this in terms of like a yield functions, because they will need these yield functions to maximize or to model the whole refinery, as we will see later on in the next classes. And then the lumping is then determined by the nature of the process. So it's how it's if what they want to see, basically what they want to see. And then it's very simple to use, but it's not that detailed, yeah, because we don't know, we cannot model the properties for these lumped components. We don't know that. So that's the lumping models. Now the molecular models is just like to me it's just like a more detailed lumping models, because we simply the even though it says molecular, but nonetheless there are thousands of molecules in there. So we don't have any thousands of reactions. So in a certain I mean to a certain extent, it's also like a lumping, but it's just like a more detailed lumping. So we use this because we want to characterize the properties, basically the properties of the stream. Yeah, properties of the, in this case, it says like the chemistry and then the molecular information of that particular stream, while the product quality, which is the properties, and then this is then the concentrations of the benzene and aromatics. And just use the same example. Okay, and then once we know this, and then we can simply trace and control the molecular flows from in and out from the refinery, and then we can then use the optimization, much more detailed information. And then yeah, if we want to like model the hydrogen, which we will see in some of the next classes, we can then trace this component as well. This one I think we have seen it. Molecular mass, yeah, molecular model. So yeah, there are so many models to predict gasoline, kerosene, and diesel fuel, but they could also do, like for example, connect this data into properties. So this gasoline, it has this and that and this and that kind of Fiona structure, and how many carbon numbers. Yeah, this is as deep as they can, and then they can then connect that informations of the C, and then the type of components, this Fiona, and then they connect it to the properties of that specific component. This is the mobile. You can read this. Yeah, to do this basically, you will need lots of data. You will need lots of efforts. And then you will need a very good team. Yeah, a very good engineering and research team supported by the company. Otherwise, you will not be able to start thinking about this. You will not be able to do so, let alone do it. This one, I think we have touched this. This is how they model the Piona, so from the gasoline fractions. So this is typical. Yeah, for example, with this the gasoline fractions or naphtha fraction from C4 or C5 until C12, this is typical. And then we can see typically this naphtha fraction or gasoline fraction, it has at the lower end of the carbon numbers, we have lots of paraffins like this one. So we have normal paraffins, we have the radix and the isoparaffins, and we have also like olefins in this case. And then, but the more we go in the carbon number, the heavier it is, and then the more we have like aromatics, like in this case. So we have aromatics, we have isoparaffins. So these two are the chunks to make the octane number higher, like we discussed like last time. And then this is then we go as we go along. Not so much, yeah, in terms of, I mean, it's not so much in terms of the mass fractions in this case. So that's the data that they have. That's how they try to fractionate the gasoline into Piona and carbon number. So it's also like a means to model this, and then from this, from here, they know, like for example, if this is then my gasoline, it has a certain Ron number, right? Ron number. It has a certain RVP. It has a certain blah blah blah, which I don't know. And then they have another sample like this, another sample, and it has also a certain RON, certain RVP, certain blah blah blah, and then they have another samples like that. And then they can then try to connect each of these samples with this data, and then they will then model that, yeah, using all kinds of regression that you can think of, or what they can think of as well. Okay, so hydrocracking pathway is just a matter of making this more detailed. So they have like a more detailed kinetic reactions, because they simply have more details characterizations like this. Yeah, so in each 1 2 3 4 5 6, there are 6 components which they can then put into this reaction path for hydrotreating, for example, in this case. I will leave you to this, and then make a comparison. Lumping, as we know it, easy to build. Molecular, you will need lots of resources and data. Less, yeah, we need less lab data. You have to have a large number of data. It's very efficient and very easy to compute. You will need more computing power for that. For easy purpose, like if you want to make like a simple refinery model and then optimize the refinery, and then you can then later on prove that optimization results by a more detailed model, which we will learn later on. So simply to get like a direction or something, this lumping model is a good way to use. This molecular is obviously it can be used for many purposes compared to lumping, and then not so much information is lots of informations as we saw earlier, and then obviously there is no interactions whatsoever. Yeah, this one it has it, and then there is no product properties like I mentioned repeatedly already. On this one we can predict the product properties. So so in half an hour, let's do this. Yeah, I will show you so I made like some dummy. We'll just use very simple one. Yeah, open your Excel. We'll use very simple one, which is in this case I believe it's three models. The three lab models, which is very easy, and it's also easy for you to follow. I put this reaction rate cases. So I have just put the same. Yeah, we have gas well, gasoline, coke, and gas. So I put it the same. So we have gasoline, gas well, coke, and gas, and then we have the temperature, the time, and then we have the measured. For example, these are the data from your plant or from your lab, whatever. So this is the data that you have, and then you say, well, I have this data in the lab, so I want to scale up this reactor, right? You want to scale up the reactor, so that means you have to use this data. But this data is like taken, I don't know, because this is the data that I generate. It looks very nice, but in reality, it will not be as nice as this one. So you have like every 10 seconds, maybe 10 minutes or whatnot. So you have like how many data points? Like 100, sorry, like 1000. So it's about 100 data points, 100 rows, yeah, 102, 101. So the question is that just like this, what this, so how much is then K1, K2, and K3? Why do we need to know that? Because once we know this, we can then design the reactor. Yeah, reaction engineering is about designing the reactor. That's basically what it is. How we then control the temperature, how we control the reaction rates. That's about this design of reaction engineering. So we need to know first and foremost the kinetic, which is then the K1, K2, and K3. So to do that, we will have to just to give you an idea. So we have what we have is the what was it again? We have gas oil, right? So let's say this is the A, and then it makes the gasoline, which is B, and then we also have like coke and gas, which is C. So this gas will it can make gasoline. This is K1. Assume K1. K1, K2, and K3. Okay. And then we have this is then K2, right? So from gas well, you can also straight make coke and this coke and gas, and then gas well can also be cracked further to make coke and gas, which is then the K3. So basically, you can imagine, yeah, you can imagine this is your time, and then if you have like a continuous reaction, a continuous concentration. So you have like a continuous reactor. This is not only time, but it's also like the length of your reactor. Yes. Yeah. So this is the length of your catalyst, basically, not the reactor. Length of your catalyst. If it goes from here and ends up over there. So this is length of your reactor. Sorry, the catalyst. So if you put the profile of these reactions, it will go like so. This then your gas will behave something like this, as I mentioned to you. First order reactions, yeah, and this A, and then your B is yeah, I don't know, maybe something like this, right? Because in the end, it will have to be consumed to make a coke and gas, something like that. And then this coke and gas eventually it will be produced from gas oil directly and also from gasoline. So it's basically this one, right? So this should be before you do anything in your data analysis. This should be what's in your head. So I should be able to get this kind of curve, right? So if you don't get that kind of curve, that means either your data is wrong or your understanding of this mechanism. Either your data is wrong or your understanding of this mechanism is wrong. Why do I have this? Yeah, because this is the mechanism. So this mechanism is wrong. Yeah, if it doesn't match your data. So let's see the data. Let's see the data. Obviously it will then match, yeah, because this is the data that I just made. So let's plot this. See, so you have 1 minute, yeah. So basically, sorry, this is then the blue one is then the gasoline. Sorry, the gas oil. So the gas oil, and then what is this? The what that color is, orange maybe, is the gasoline, and then this is then the coke and gas. So the data is until 1000. So yeah, it's kind of like a fix. I mean, kind of like a similar with what we have over here. So it's going down. It's the other way around apparently somehow, because it's just a dummy example that I make. And then we have this B, which is this one, the gasoline, and then we have another one which is like a bit like late, like that one. Okay. So the question is that so what is that now the K1, K2, and K3, K1, K2, and K3, right? So that's the questions. So you could then solve this with the concept of this optimization. Okay, so how do we solve this? Basically, okay, well, maybe I'll write it here. Control N. So how do we okay, so we have gas oil, right? K1 gasoline, and then the coke and then gas, like A, B, C goes here. This is then K2, K3. So our chemical engineering knowledge tells us that dCA per dt equals to, because this A is going to be reacting to make gasoline, and then the B to make B, and then to make C, yeah, via these two pathways. So it will then be reduced by K1 and then B, and then reduced by K2 and then C, right? So these two. And then the other one, which is then the B, so that dCB dt, or dB dt, make it B. This is then make it A. And this is then equals to, well, B. You make B from A, so that means by K1, K1A minus, because you are making C from B, so K3C. And then the C dt, the other product here, over here, you just simply make it's a product of A plus a product of K3 of B. So this one, yeah. And then because we're going to solve this in a simple way using what was it again, using Excel. So we need to do a simple integration. So we use Euler method. Well, just Google that Euler method, and then we will then simplify this to make like a dc delta C delta A for delta T equals to minus K1B minus K2C, and then delta A, you can argue that this is then a t minus a t minus 1, or a0, make it something like that, and then delta T, yeah, and then minus K1B minus K2C, and then A equals to A0 times sorry, not times, minus delta T K1B plus K2C. The same goes with this B. So so you could say that B equals to B0 times delta T Q1A minus K3C, and then C in this case is then C0 plus delta T K2A K3 B. Okay, so these are the three equations that you will need so that you can either code that or program that in Excel or in any other language, and then you will then try to find how much is then K1. I don't know what happens. Find how much is then K1, K2, and then K3 in such a way that all the data match with this calculated value, because we're going to calculate this ABC, and it has to match the data over here. The other one, the data over there. So I will let's do it in 20 minutes, see if we can do so. 1 minute yan. Okay. How do I? Nah, so we have T, yeah, as one or whatnot. So now we can say, yeah, put it here. I don't know, put it there. So we have now, so we can say, I need to have like some space here. I'll tell you why. So we will have like K1 and K2 and K3. And then we have like this T, the same T. And then we have this A, which is gas oil, B is then the gasoline, and then C is then the coke and gas, and then we have this equals to 0. And then we will then start, well, in this case you could start with 10 or whatnot, but then we'll start with 1, because this Euler calculation, it's very sensitive to the delta T. So if you have like a too big of a delta T, the calculations will be wrong or inaccurate. But you have a very small of delta T, you will need much more memory to do so, and much more computing power. So in this case, because it's very simple, we will use in 1. Yeah, but this is something that you have to do trial and error on it. But since I make the case, so I know. So A is then, so we assume it's the same. Yeah, basically. Has I put some curvy thingy. So if we say, well, I know for sure in this reaction this guy should be like 100, and this should be like a 0, and that should be like a 0. I don't know. Or you can also say, well, this one is over here. Up to you. Yeah, what do you want to do? This one as well over here, because we know we use this as a data. It's up to you. And then the A in this case is that A is then A0 minus delta T, which is this minus that one, multiplied with K1. So in this case, K1 is over here, and then times B, which is this one, and then plus K2 times C, which is this one, right? I8. Okay, so that's your what was it again? The concentrations of A at time 1. And then the same with B. You can also say, well, B equals to B0 plus, delta T K1 times A minus K3 times C. Okay, and then C0 plus delta T we do it in this way so that you understand how it works. K2. So if you have if you get sorry K2 A times A plus K3 times B, right? Yes, yeah. So you can it's 1000, right? So yeah, put 1 2 and then you can then say, okay, now I want to have it like a 1000 anyhow, yeah. And then you model this okay, and then you calculate the A B C 1000, okay. You could also do like oh sorry, it's all the same because it's so we okay, let's just put I don't know K1 K2 K3, put 1 1 1, and then you have very strange numbers, so don't put 1 or 0 1, so that you can have like 0 0 1 and then 0 0 0 0 1. And then now the number seems to be like something that we can control, and then you can then play around, yeah. I mean yeah, so 15 more minutes. You can then say, okay, now I have this is then at time 0, this is then my number, and then it matches with this one, and time 10, so this one it has to match with these numbers. Can you see? So the data is 104, but then our calculated data is 99, and this one is 5 while it's 17. This is 4, this is 10. So this is not correct. Well, we know it's not correct, so the question is that can we make it correct? So we need to first establish a connection between this 10 and 10 and then 20 and then 20. So how do we do that? Let me think. So the A data, B data, C data. Do VLOOKUP, this one, and then the table array is over here because it's the data, and then we make it like fix, and then we have this has to be like an F, okay, and then column for A is column 1 2 column 2, and then false. I don't know what this is, but one thing I need to caution you is because we are doing this so A is then depending on B and C, and then the B is also dependent on the A and C, and so on and so forth, so they are like intermingling. So Excel can solve this problem easily nowadays. You go to options, you go to formula, you enable iterative calculation. So I'm also wondering why I could get the answer. I mean, I could get these calculations suddenly. You enable the iterative calculations. If it's not enabled, I mean, Excel will cry. So you have to enable this iterative calculation. Hence, you get these calculations already. And then this one is that one. And then this is then the column number 3. Yeah, 3. This is then column number 4. Okay. Right, so you can see the data is this one, so it's the same, which is the same as this one, and then you can say, well, error. Now let's make it square error, so that you know this is then this minus that one square, so you know. And then the B and C, anyhow, B error, C error. So you have you can you do this? Let me check. Yeah, this one. Yeah, so everything seems to be correct, and then right. So you have this 10. This is the data 104, 4, 5.2, and 4.6. So can we sum them? Total error. Can we sum this? No, because we have nah. So that means we will have to what do I sum? All right. J7 this otherwise, right? The same, right? Yeah, can we do so? Why not? No, if I put like not that one but 0, it becomes a number simply because we don't have the data. Sorry. Can you why this is not the case? Sum. What happens? Why can't we sum them? If I sum this, double sum, it should be able to sum, no? Right now. So I don't know what happens to you. Alright, so I sum. Anyhow, let's see what happens. Oh, 100. Okay, so this one, this is alright. Okay. Apparently, up until means up until here, then up until here it's 140. And the 140 and something that you can then later on. So you need to remove this, and then you get this sum plus sum plus sum. Right, so now you can either make it square root or just simply do this sum. So let's try to make a plot yeah, so that you can see. I have now add a and sorry, I'll have to switch this into change that type into that one, right? Yeah. And then and add a series is always time, right? And then this is then the calculated value, something like that. And then b, and then x is something like this, and this is then the y for b, and this is then c. This is then, so we would expect that this graph, okay, so the yellow here, the a, we would expect that the a, that this blue, this becomes blue, this is then we have like a, so that I can line, right? So let's see, that line, this is also a line, I don't know, you can do this better, yeah. There's a like a line, sorry, line, and then you change it to gray. I don't know, so that you know. This one you change it to blue. That one, and this one you change it to fill. No, this one, then this one. Okay. Anyhow, this is the blue. Something like that. I don't know. Yeah, what happens? Yeah, I mean, it doesn't calculate until 200. Nonetheless, we just need to make sure that this guy fits to that, and this guy fits to this, and that guy fits to the that gray. So what we do, we'll look into why it doesn't calculate up until the end. We use the same, but we know that this is going to be like a non-linear, yeah? Because of the calculations and stuff. So what we want to minimize is this one, objective function. We want to minimize it. What do we want to change? This guy. And then any constraints, as far as we know that this thing has to be like positive. That's basically what this is. And then okay, and then non-linear, and then we try to solve it. Yeah. Where is that thing? See, so now you can see in the first trial you can see that this is then the blue then try to match with that, and then the yellow the orange is trying to match with that, and then the gray is trying to match with that. So in this first instance, this is then the first trial. So what we need to do further is then to make sure that these calculations go up until 1000, which we don't know why. I don't know why I have to. Let's see what happens here. If I move it down, what will happen? Oh, we can go. Oh, okay, then I can go up until 1000. Okay, so I can see. I don't know what happened. Sometimes things behave very strangely. This is until. Let's make it until 1000. 1007. 1007. 1007. 1007. It's much easier to do this in Python or any other or MATLAB, but this is just to show you. right? So now we do this again. Let's solve. There is oh, the graph, sorry, this A is 1007. Okay, this then 1007 as well. Okay, now voila. So this is then the kind of if you see this, well, the graph looks okay, so to say, but this one is then going down, which is, it doesn't fit to the to the data, and then it's the K2, because it's basically on the gasoline part, right? So the K2, it's very strange. So if we can then try to find, so let's see if I have this thing, the 0.001, this one I don't know, try to put it like, I don't know, put it like 5. This one I keep it that way. Can we see this one? So that's the results. So if I can then use different, right? You understand what I'm doing now, yeah, here, yeah. So what I'm doing is that try to get this guy, if it's somewhere here, try to put it over there, and or if it then try to put it over here and there, in such a way that it can find the optimum value, or in this case the minimum. This is minimum minimization. So it's if you flip this the other way around, if you flip this way, so we'll then try to find the minimum value over here. Okay. So we then place this guy, the starting points, basically at the different locations, in such a way that we can then try to make this graph as close as possible to the data, and then make these numbers as realistic as possible. So that's what we can do iteratively, and then once we are happy or content with that, and then we can then use these numbers to design our reactor or to move forward, right? So in this case, well, you can see somewhere here, but if we yeah, this part is not really nice, but I will leave you to that. Yeah, if, we are now in the time limits, so do this on your home. So here I have shown you how to work with this lump model, and I've shown you how to use solver for this particular lump model approach. And then this is the skill that you can bring to your company and plant, and then you will do it on your own. And then if you want to discuss it with me, please go ahead. We have this WhatsApp. So do you have any questions? You have 1 minute to ask any question. Any question? No. Well, if not, then I will see you next 2 weeks. Yeah, next week I will not be here. So next 2 weeks, make sure that make sure that make sure that the oh, how do you call it? You can get access to the UTP computer, and then try to play around with symmetry. Okay. So I wish you have a good weekend, and then try to do this on your own, get some skills, and then if there's any question, just let me know. Okay.